Okay, let's begin. Good morning, everyone. So today I'm going to talk about race conditions in JavaScript apps. And so the title of this talk is about race conditions. Today I'm going to talk about other things as well. Maybe other edge cases that are not strictly race conditions, but you may encounter them when you write asynchronous code. So before I begin the talk, I would like to share a bit of story before, like how this talk came to be. So I first got the idea for this talk on one day. On that day, I went to a local meetup in Thailand, and after the talks are done, it's like networking time, and my friend approached me and asked me, "Hey, Thai, is it hard to deal with race conditions in JavaScript?" So I answered, "Well, it's actually pretty easy. You just don't forget about them." He gave me a bit of a confused look, and I was like, "Hey, I'm totally serious here. Let me show you a couple of examples." So I took out my laptop and started coding, showing him some examples. And before long, it turned into a really deep discussion. So after that discussion, my friend told me, "Whoa, this could have been a full talk. Why don't you make a talk out of it and submit it to JSConf or something?" So here I am, and a big shout out goes to James for giving me the inspiration for this talk. He's with us here as well. So next time you have a deep technical discussion, maybe you can tell your friend to consider submitting a talk. So this makes it my second time speaking here at JSConf.Asia. So big thanks to Thomas and all the organizers involved in running this conference. It's really great, and thank you for having me once again. So today I'm going to show you two stories from my experience dealing with race conditions and stuff. So I hope you can learn something out of these stories as I did. By the way, my name is Thai, and I'm from Thailand. My Twitter handle is @dtinth, and if you have any feedback about this talk, please send it to me, and I would really appreciate it. I'm currently working at Taskworld as a front-end architect, and I'll get back to that later. But now, here comes the first story. And this story involves a little search box. So in this search box, as I type a keyword, it's going to show the search result. And it's going to show the result instantly, so I don't have to press enter or anything. It's like Google's auto-suggest. So let's build this real quick. First, we need the markup. So here, I'm going to use a section for the wrapper. Then there's an input box right there. And then a list containing the result. So that's all the markup we need. Next, we're going to add some interactivity. And for that, I'm going to use Vue.js. So let's start with the data model for our state. First, we need to store the search query that the user typed. And we can bind that to the input box using the vmodel directive. Then we also need to store the search result to be displayed on the list here. And to do that, we can use the v-for directive to do the binding. And finally, we bind the content of each result into the respective elements. So the data and the DOM, they are now kept in sync. So when the user enters the text query into the input field, it's going to update the text right here. And we can watch for when it changes. And when it changes, we can perform an asynchronous query by calling the search function right there. It's going to return a promise, so we have to await it. And once the result arrives, we save it into the state, which will be displayed on the user interface. So there we have it. And let's see how it goes. So, OK, I'm going to type in React. I don't know why, but OK. So the result shows up, and that's good. But it seems that the result that I see here doesn't have anything to do with React. So what's going on here? Let's try again, but this time I built an inspector on the right so that we can see what's going on. OK, uh, you can see here that the result I want to see is overwritten by the result of the request that I made earlier, but it finished later. So it overwrites the DOM. And this kind of makes sense because the shorter the query, maybe it will return more result and maybe it will take longer to load. So you cannot depend on the order of the request to correspond to the order of the response. So you can think of an async function as a function that spawns a thread. And the DOM here is a shared mutable state. So when dealing with shared mutable state, we have to be careful. So let's come back to this code. When we face problem like this, one of the common approach I see very often is to do a debounce. And what I mean by debouncing is that instead of doing the search right away, we're going to wait a bit until the user has finished typing. And after that period of inactivity, then we do the search as usual. So let's try it. OK, it seems to work. Because now it only performs a single request, there are no more competing requests. But even with the debounce, it still doesn't guarantee the order of the response. So I could do something like this, then we're back to the same problem. So let's step back and look at this code again. The real problem here is that while we are waiting for the result to arrive, I could have triggered another search. And in this case, when the result did arrive, it might not make sense to use it anymore because now I have already triggered another search. So let's fix this, but first I'm going to get rid of the debounce because it didn't work. Instead, I'm going to generate a unique ID for each request, then keep track of the latest request ID here. And after we await, maybe this latest request ID could have changed. So we compare. If the request ID we are holding on to doesn't correspond to the latest request, we'll just discard the result. And let's see. OK. Now it works. And because we only care about the result of the latest request, other response got discarded. But here, now I am searching really slowly. And you can see that until I finish typing, I get no feedback whatsoever from the search box. And that makes me feel that the search box is a bit unresponsive. Because before the result could arrive, I type another letter. So it discarded the result, the interim result. But if we compare that to Google, even on a very slow internet, I still get the result as I type, even if it lags behind by several characters. So it's clear that they are not totally disregarding the result that is not the latest. So I think we can do better. So instead of discarding the result that doesn't correspond to the latest request, what if we only discard the result that arrived out of order? So we can do this, and let's see. OK, now it seems to work. And you can see here that I get the result I want even before I finish typing. So yeah, you can see that this humble little search box, it took me 3 attempts until I can get it right. And that brings me to the first takeaway for this first story, which is to always remember about the potential REST conditions whenever there is an await call. So each time you see an await, maybe think about what else could happen while we are waiting for the result, and also think about whether or not it makes sense to use the result after the await. All right, that's the first story. We're going to continue with the second story. And this story came from my experience working at Taskworld. And it is a real-time collaborative project management app. And that's important, and you'll see why. The story happened when we built the app in its early days. So we're just starting out there. It happened about 2 to 3 years ago. And it has to do with something called optimistic updates. So for example, our app provides a Kanban board. And suppose that you drag a task from one list to the other. You wouldn't expect the task to go into the loading state, right? Well, no, you expect the task to just snap right into the new list. And that's what optimistic update is. So basic idea is we update the UI first in anticipation that the request will be completed successfully, and while we synchronize the change with the server in the background. So having this kind of experience, like optimistic updates, is really important for collaborative applications. But our app uses React, and when we use React, we like to derive our user interface from the underlying data model. So in this case, it's the Redux store. So in order to preserve the unidirectional data flow, we update the data model instead. And we're going to let it flow into the UI. And for this example, maybe moving a task is a bit complex operation because it involves both a task and the list. So instead, I'm going to just focus on something simpler such as renaming a task. So when I hit enter here, it's going to trigger an event handler, and it will call a function here, rename task, which is our action. And following this basic pattern, what we did is, okay, we update the data model here, and that's going to cause the data model to flow into the user interface, and like that. Then we make the API call to synchronize with the backend. And because sometimes internet connection may not be stable or something weird is going on with the API, we use a try catch to display the error message, just for good measure. And that's it. That's how we implemented basic optimistic updates. And for most of our operations in our app, we write code following this basic pattern. And this works really well and gives us a really great experience as long as nothing goes wrong. So it works well in the early days when we're just starting out, and our focus was to figure out how we can make a project management tool that our customers would like to use. However, as we get more customers, we start getting reports such as, well, our screens are displaying different things. They become inconsistent. Or something more severe, such as this one. So someone writes a comment, the other person didn't receive it because it never gets sent, but the app acts as if it was already sent. So, work is lost, and that's pretty serious, I think. We came back to our code, and it became clear that our implementation of optimistic update was indeed too optimistic. So there's no room for anything to go wrong here. And when it does, let's see, for example, if this API call fails, first, we didn't revert our data model back to the previous state. So each client will go its own way, and it will be totally out of sync. And we also didn't retry the request. And this is really bad because, we tried so hard and put in a lot of effort to craft a great experience that the customer will want to use, and now we're just throwing their data away. And that's not what we want for our users. But well, that was what we implemented. So at that time, we incorrectly assumed that building a single page, real-time, collaborative app and task management apps, it's just like CRUD apps, create, read, update, delete. That's mostly what it does. So it should be as simple as an old school multi-page application, because that's what we know, that's what we're familiar with. And if you write Ruby on Rails, yeah, doing a create thing is just as simple as that. So it's supposed to be simple, right? Well, maybe not really, and now here we are facing its consequence. So we have to fix it, and that means we have to go back and fix all of these operations that we've implemented so far as well. So our goals shift. Data loss is a serious problem, and first, to fix that, we need to try to achieve eventual consistency. That means everyone will eventually see the same thing on their screen, which I call the ground truth, without having to press refresh. And second, we want to prevent data loss as much as we can. So let's first talk about the first one. Coming back to this code, recall the previous part where I say when the API call failed, we didn't revert the state, right? Maybe that's quite easy to fix, right? We just store the previous title here, and when there's an error, we just revert. And that would work. Or would it? As we learned from our first story, you see and await, and anything could happen here, especially in a real-time app. So, for example, someone may successfully update this task while we are awaiting here, and that means the previous title that we stored will no longer become valid, and we cannot use it anymore. So, the more edge cases we try to solve, the more they seem to come up. And what about more complex operations, such as moving a task between lists? How much complex would our code be if we were to handle all the edge cases in all of these operations? Or is there something fundamentally wrong with the way we are writing code? So I took another step back and think about the way we are approaching optimistic updates. And then I realized that if we want to have eventual consistency, we must try to stick with the ground truth. I define it as the letter state that we receive from, or the thing that was acknowledged by the backend can be considered the ground truth. And each time we update the model optimistically here, we are moving away from that ground truth. And considering that everything else may be going on and happening all around, that will make it harder to ever come back to it. So maybe we should leave that data model alone and don't update it optimistically. But then, how would we implement optimistic UI? Then we figured something out. What if we had a separate data model representing a list of the pending operations? Instead of optimistically update the data model directly, we just add it to the list of pending operations. And when it's done, we just remove it. When we render the UI, we overlay the pending change on top of what's inside the model, essentially computing a projected optimistic version of the task on the fly in our components. And that could work because if the operation fails, the data model would be left alone and the UI will revert back. But if the operation succeeded, the ground truth will be updated first, then the operation will be removed from the list. And from the UI perspective, it's nothing changed. So now we have a data model that allows us to do optimistic updates without driving us insane. So now let's consider a case where I just created a task here. And the blue bar right there represents the time it takes for the operation to complete. But now, since we have optimistic update, I see the task appear right away. And that means I can also interact with it. So let's say I immediately assign someone to that task. In this case, this API call would fail because at this time the task doesn't exist in the backend yet, right? So that will lead to a data loss, and we don't want that. And that means I need to wait until the previous operation complete first before we can work on the subsequent operation. And that essentially means we have to sequence our operations into an operation queue. So with the operation queue implemented, the action code now looks like this. So this is now even simpler than the first one that we came up. And we just let the queue do its thing. So now all of our write operations can be fixed by making it write to the queue instead of calling the API directly. Then we can update the UI to compute the projected state by reading from that queue. So because the operations are now sequenced and managed by the queue, that means it can also take care of retrying the failed request. And that helps us deal with data loss. So we haven't covered all the edge cases yet, and preventing further data loss from here is like just a matter of asking a series of what-if questions. For example, what if the user closes the browser while the queue is still running? Well, we can try to prevent the user from quitting the browser, or we can persist the content of the queue into the client-side storage so that it can be resumed afterwards. Or we can do both, right? But our user may be using our app from a mobile device, and it might not be practical to do that. So we decided to also save the queue to the client storage. And that gave us, as a bonus, gave us a building block that if we want to make our app work offline in the future, because progressive web apps are becoming more popular each year. So yeah, that's a good bonus for persisting the queue to the client storage. But then a user may be running our app in multiple tabs. So before we decide to persist the queue, there was no problem because each tab would have its own queue. But now the queue is persistent, so it becomes a shared mutable state here. If every tab runs the queue at the same time, bad things going to happen. So there can be only one tab that runs this queue. But which one? So today, with today's web technology, we have shared web workers and also service workers. So we have two things. So maybe we don't need any tab to run it at all. We can just do it in the workers. But today, we also have this. So I guess we cannot use the workers yet. So we have to make it so that any tab can work on the queue if and only if no other tabs work on it. But since our client-side storage can be asynchronous, there might be the case where more than one tab looking at the queue and saw that no one's running the queue, and both decide to work on it. So who wins? And there can be only one tab working on the queue. That's a hard requirement, otherwise bad things gonna happen. So we use a shared client-side storage and have each tab write its own ID to this storage. And after a while, we read it back. So the latest tab to write wins. And the winning tab will periodically report its status to the shared storage so that other tabs know that, okay, someone is taking care of the queue and is still alive. But what if that tab somehow disappeared? Maybe the user closed it, maybe it crashed. Then we have to set up a timeout so that other tabs could decide that, well, the tab that originally worked on it has gone and can take over. Can take over the work left from the previous tab. So, but what if the tab that disappeared didn't went away? It just slept and it came back. So we also have to handle the case where while the queue has been taken away from the tab that is not dead. So as you can see, there was a lot of edge cases that we have to handle to make our app more resilient and to prevent data loss. That brings me to the takeaway that first, I didn't know that writing a CRUD app would have to be this complex. You know, there's a lot of tutorials out there teaching you to like how to make a real-time to-do application collaborative using, let's say, Socket.io. I've never seen any of them warn me about this. So these are the problems we face when we try to build production quality apps. And that's why I want to give this talk so much. And the next takeaway is knowing your tools can help. So there are higher level primitives that can help you write code that's free of race conditions. There are some cloud providers and SDKs that will take care of these problems to some extent. Some open source databases are designed to be able to synchronize and work offline. So sometimes, if you can take advantage of them, that's great. You have less problem to solve. But sometimes your circumstance might prevent you from using the tools that you want. And that's why, in my opinion, the most important thing here is to become aware of the existence of this class of problems. Because even if you don't know the solutions or if you don't know which tool to use, at least you know that you should try to avoid it. So to close this talk, I would consider this talk a success if you go home today and become more careful when you see the keyword await in your code base. You don't have to be paranoid. Just be aware that during an await, anything could happen. I don't know if that's paranoid or not, and maybe when you test your app, try double-clicking everything instead of single-clicking. And the next time you see or write the word await, I hope you think about this talk. Thank you.